Okay. Now students, then you know the noise behavior and what is noise. Now any signal other than the wanted signal which is called as noise, and what are the different types of noises, internal noise, external noise, and what are the noise which is mostly affected in our communication system is nothing but internal noise. That internal noise is also called as a thermal noise. You know all the behavior of noise and the definitions and everything. Okay. Now we will see that noise effect in analog modulation technique. Okay. Now that noise effect in analog modulation technique. Now see, just this is the transmitter portion, message signal. Now first I want to band limiting the low frequency information, therefore low pass filter. Now this message signal and modulator with the carrier, modulated signal. But when it is modulated signal is transmitting through the channel, definitely it is affected by noise. That noise is nothing but which noise? Thermal noise, white noise, additive white Gaussian noise. Okay, the thermal noise or white noise or additive white Gaussian noise, or we call it as a white band noise. You know that. So this is that modulated signal is affected by noise. This is white band noise. But when it is passing through the filter, because the input to the receiver is a band pass filter, then this white band noise will be converted to narrow band noise because there is a filter, so it will be eliminated. Okay, white band noise will become narrow band noise. So you know what is a mathematical representation of narrow band noise and all these things, you know that. Okay. Now anyway, we'll start here. So what is a modulated signal? Now this is the modulated signal. The modulated signal is a DSBSC signal. What is a DSBSC signal? Message signal multiplied with carrier, AC cos 2 pi FCT. Therefore, now signal power SI. What is the signal power? Power is nothing but mean square value SS square of T. Now I am giving one shortcut method also. Whenever the power is nothing but mean square value, right? Now a mean square value is nothing but x square of T square. You just square it. Okay. So that is a easy method. So which is nothing but expectation of m square of T, and for this AC square cos T is 1 by 2, right? 1 by root 2 whole square. Now this is 1 by root 2 whole square means 1 by 2. So now see here, this is nothing but AC square by 2 is constant, expectation of m square of T, message signal power, right? Now which we can represent it as AC square by 2, expectation of m square is message signal power m. This is the signal power, okay, due to the modulated signal. Right. Now what is Ni? Ni is a noise power due to the message signal bandwidth. Okay, this is common for all modulation technique because any modulated signal is generated with the help of a message signal is required. Now due to this message signal, then one noise is nothing but the noise power due to the message signal. Now that is N naught into omega watt. Therefore Ni, which is equal to N naught omega watts. Okay. Now what is the signal to noise power? What is the signal power to the noise power at the input of the receiver? Okay, this is output of the transmitter, which is input to the receiver, which is nothing but AC square PM by 2 N naught into omega. Now come to the receiver side. Okay, now receiver side we will see one by one. This is the signal power to the noise power. Signal to noise ratio at the input of the receiver is AC square PM by 2 N naught into omega. Now this is the modulated signal is passing through a wideband noise. Now this is the wideband noise. Now when it is passing through the band pass filter, then it will become the narrow band noise. Now what is the output of band pass filter? The output of band pass filter at the receiver is DSB-SC signal plus narrow band noise. Now what is the DSB-SC signal? AC m of t into cos 2 pi fct. Now how to represent a narrowband noise mathematically, which is having two components, one is in phase component, other one is quadrature phase component. nc of t into cos 2 pi fct plus nq of t sin 2 pi fct. Now this is nothing but AC m of t plus nc of t into cos 2 pi fct plus nq of t sin 2 pi fct. Now this is cos 2 pi fct and this is sin 2 pi fct. Now see here. Now this is the output of the band pass filter. Then going for the process of demodulation. This is the demodulator. Right? What is the demodulator? The demodulator is nothing but synchronous detector. Now what type of demodulator it is? This is a synchronous detector, coherent detector. Demodulator, which is synchronous detector. Right. Therefore, now this is multiplied with output of multiplayer. Output of multiplayer at the receiver is, all or everything is output of the multiplayer, which is AC m of t plus nc of t into cos square 2 pi fct plus nq of t cos into sin. Now this is sin 2 pi fct into cos 2 pi fct. If I multiplied and divided with 2, this is 2 divided by 2. Now see here, cos square theta can be written here as AC m of t by 2 plus nc of t by 2 plus, now this is AC m of t by 2 plus nc of t by 2 into cos 2 pi into 2fc into t plus nq of t by 2 sin theta cos theta sin 2 theta sin 2 pi into 2fc into t. Now this is the output of the multiplier. Then this is passed through low pass filter. When it is passing through low pass filter, the low pass filter will not allow this 2fc term. The low pass filter will not allow this 2fc term. Okay. So now what is the output of the receiver? So now output of the receiver, this is the output of the receiver. See here, this is the output of the receiver. Now this is output of receiver. The output of the receiver. Now this is signal part. This is noise part. Okay. Now the output of the receiver is, this is the signal component, this is the noise component. Now this is the signal, this is the noise. Now I want the signal power at the output of the receiver. At the same time noise power at the output of the receiver. Now you tell me, this is the signal component. So what is the signal power? I find here. The signal power S0, which is equal to expectation of square AC square by 4 m square of t, which is nothing but AC square by 4 expectation of m square of t is PM, power of the message signal. Right. Noise power. Now what is the noise power? Noise power at the output of the receiver is expectation of nc square of t by 4. which is equal to 1 by 4 expectation of NC square of T. Now this is the noise power. What is a noise power? When the noise is passing through a band pass filter for a DSBSC signal, which is already calculated. Now how much it is? 1 by 4. Then this is calculated for a DSBSC signal 2 N0 omega. Now see here. Now what is the signal to noise ratio at the output of the receiver? The signal to noise ratio at the output of the receiver, which is nothing but, now 4 cancel, AC square PM by 2 N0 omega. This is the signal to noise ratio at the output of the receiver. This is the signal to noise ratio at the input of the receiver. You know that this is the receiver. This is the receiver output. This is the receiver input. You know that what is the signal to noise ratio? Signal to noise ratio at the output of the receiver to the signal to noise ratio at the input of the receiver is called as figure of merit. Okay. Now the signal to noise ratio at the output of the receiver and to the signal to noise ratio at the input of the receiver is called as figure of merit. For a best system, the figure of merit should be as high as possible. Okay. Figure of merit should be far greater than 1. But what happened here? So this is the signal to noise ratio at the output of the receiver and this is the signal to noise ratio at the input of the receiver. Both are same, AC square PM. Therefore, what is the figure of merit? The figure of merit which is equal to 1. This is the figure of merit which is equal to 1 in DSBSC. So what is the meaning of that? In DSBSC, now in DSBSC, signal to noise ratio at the output of the receiver which is equal to signal to noise ratio at the input of the receiver. There is no improvement. What should we do? Now the signal to noise ratio, the signal is transmitting by the transmitting antenna, is passing through the communication channel. Now the signal is entered at the input of the receiver. So this signal is affected by noise, therefore it is having some signal to noise ratio. What should we do? Your receiver doing such a procedure, your receiver, whatever the receiver will do that. Whatever the signal to noise ratio is coming at the input of the receiver, it should be improved version when it is coming at the output of the receiver. Am I not? See here, the noise is affected and some ratio is coming. So in the receiver, you do something such that that signal to noise ratio should be improved when it is coming at the output. So what happening in DSBSC? Whatever the signal to noise ratio coming at the input of the receiver will be maintained same signal to noise ratio at the output of the receiver. There is no improved version. How much is noise affected? The same noise effect will be available at the output side. Is there any improvement? No. This is the figure of merit which is equal to 1, which is not good. Figure of merit is far greater than 1, is a good for a best analog modulation technique. Okay. This is the way to calculate the figure of merit of DSBSC. This is the figure of merit of DSBSC and this is the noise analysis of analog modulation technique, and I am choosing one modulation technique which is nothing but DSBSC. Okay, we will see one by one. First you note on this. Okay, this is the figure of merit of DSBSC. Now we'll do it for SSBSC signal. Now this is SSBSC modulator. Now this is an SSBSC signal. What is SSBSC signal? Now SSBSC signal is S of t equal to AC m of t cos 2 pi FCT plus AC by 2 m cap of t sin 2 pi FCT. So this is the signal power Si, which is equal to expectation of S square of t, which is equal to AC square by 4 into 1 by 2 into m square of t expectation plus AC square by 4 into 1 by 2 into expectation of m cap square of t. Now which is nothing but now AC square by 8 AC square by 8 into PM plus AC square by 8 into PM. So AC square by 4 into power of the message signal. The noise power is same due to the message signal. So this is nothing but AC square by 4 N0 into omega into PM. This is input side. What about the output side? Now this is an SSBSC signal, wide band noise, when it is passing through band pass filter, narrow band noise. So this is an SSBSC signal, which is nothing but AC by 2 m of t plus narrow band noise directly I am adding AC by 2 m of t plus NC of t into cos 2 pi FCT plus AC by 2 m cap of t plus quadrature component NQ of t into sin 2 pi FCT. Now this is the output of the multiplayer. The output of the multiplayer is means then this is the local oscillator. So cos a square, right? Now this is AC by 2 m of t plus NC of t into cos a square theta cos a square 2 pi FCT plus AC by 2 m cap of t plus NQ of t into, now this is sin 2 pi FCT into cos 2 pi FCT. Now if I multiplied with 2 divided with 2, if I multiplied with 2 divided with 2 sin theta cos theta, right? Now what is the output of the multiplier here? So output of the multiplier is output of the multiplier is AC by 4 into m of t plus NC of t by 2 plus this into cos 2 pi into 2 FC into t plus AC by 2 m cap of t plus NQ of t 2 sin theta cos theta sin 2 theta sin 2 pi into 2 FC into t. So what is the output of the receiver finally? The output of receiver, output of the demodulator, output of low pass filter, or output of output of the receiver finally. The output of the receiver is, the receiver will not allow this term, 2FC term will not allow this term. So this is the only component. What is this? This is nothing but AC by 4 m square of t, m of t plus nc of t by 2. Now this is the signal component. This is signal component and this is the noise component. Okay. So now what is the signal power? The signal power, which is nothing but AC square, 4 square is nothing but 16 m square. So AC square by 16 into power of the message signal. And similarly, now this is nc square by 4, 1 by 4 into nc square of theta. Now 1 by 4 into n square of, now expectation of noise. Now this is a noise power in SSBSC. When SSBSC is passing through a band pass filter, the noise power, which is nothing but n naught omega, right, which we already have, n naught omega. Now what is the signal to noise ratio at the input of the receiver is AC square PM by 4 n naught. What is the signal to noise ratio at the output of the receiver? The signal to noise ratio, this is the signal power, noise power. 16, 4 cancel. So which is nothing but AC square PM by 4 n naught omega. This is signal to noise ratio at the output of the receiver. This is the signal to noise ratio at the input of the receiver. Now what is the figure of merit? Figure of merit of SSBSC. Now the signal to noise ratio at the output of the receiver to the signal to noise ratio at the input of receiver is same. Figure of merit is 1. So in SSBSC there is also not an improvement. Signal to noise ratio at the output should be same as that of the signal to noise ratio at the input side. Okay. Now this is the figure of merit and a noise analysis in a SSBSC modulation technique. Okay. Note down. Clear or not? So this is the figure of merit of SSBSC signal. Okay. Now this is very easy. If you understand the noise behavior, you can easily understand. Okay. Now we'll see the amplitude modulation. Okay. Now this is AM modulator is nothing but square law modulator or switch modulator. This is AM signal. Now what is AM signal? Now this is an AM signal, amplitude modulated signal, AM wave in time domain, AC cos 2 pi FCT plus AC KA m of t into cos 2 pi FCT. Now what is the signal power? SI, which is equal to expectation AC square, this is 1 by 2, square it, expectation AC square KA square cos is 1 by 2, expectation of m square of t is PM, power of the message signal. So what is SI? SI, which is equal to AC square by 2, if you take it as a common, 1 plus KA square into PM. PM is power of the message signal. And what is NI? NI is already, you know that, n naught omega. This is the noise power due to the message signal, right? So what is the signal to noise ratio? The signal to noise ratio at the input of the receiver is AC square by 2 n naught omega into 1 plus KA square into PM. Now then this is AM signal is passing through the channel wideband noise, AM wideband noise, band pass filter, therefore AM narrow band noise. Therefore this is the AM signal plus narrow band noise. Now this is the AM signal plus narrowband noise is AC by 2. We'll write once again, not a problem. Now AM plus narrowband noise. Now therefore, which is nothing but AC plus NC of T. Sorry, AC plus AC KA M of T into cos 2 pi FCT plus on NC of T also, right, plus NC of T. All these are cos common parameters, cos 2 pi FCT plus, and now this is only a single one, NQ of T into sin 2 pi FCT. Now this is the output of band pass filter. Now what is a demodulator? Here demodulator is not synchronous detector. Okay. Now this is the AM. So the best demodulator for AM is envelope detector. Therefore this demodulator here is envelope detector. Envelope detector is available here. Envelope detector. Now what is envelope detector? Now you apply here. So the demodulator here is envelope detector. Now this is the demodulator. Now the demodulator here is envelope detector, right? Now you tell me here, this is A cos 2 pi FCT plus B sin 2 pi FCT. A cos 2 pi FCT plus B sin 2 pi FCT is the input to the envelope detector. What is the output of the envelope detector? The output of the envelope detector is square root of A square plus B square. The input to the envelope detector is A cos 2 pi FCT plus B sin 2 pi FCT, square root of A square plus B square. Now which is nothing but square root of A square. What is A square? Now see here, this is AC plus AC KA M of T plus NC of T square plus NQ square of T. Now see, this is the signal component. The noise is not separated, the noise is there in the signal, okay, and this is the large value. When compare this is negligible, neglected, because this is a high value, compare with that is neglected. So what is the output? Finally the output of the envelope detector is AC plus AC KA M of T plus NC of T. Now this is the DC component is eliminated, not a problem. Therefore this is message signal plus this is the signal component and this is the noise component. Okay. Now at the output of the receiver, so we find what is the signal power. What is the signal power? Now the signal power is S0, which is equal to AC square KA square expectation of M square of T, which is nothing but AC square KA square into PM. Now noise power at the output of the receiver, which is nothing but expectation of NC square of T. Expectation of NC square of T is in AM and DSBS is same 2N0 omega. Okay. So now finally, what is the signal to noise ratio at the output of the receiver? the signal to noise ratio at the output of the receiver is AC square Ka square into Pm by 2 N0 omega. Now 2 N0 omega, 2 N0 omega cancel. Then what is the figure of merit? The figure of merit, a figure of merit which is equal to signal to noise ratio at the output of the receiver to the signal to noise ratio at the input of the receiver, which is nothing but, now 2N0 omega, 2N0 omega cancel, AC square cancel. Now which is equal to Ka square into Pm by 1 plus Ka square into Pm. This is the figure of merit of AM. This is the figure of merit of AM. What is PM? What is the power of the message signal? Now see here, the power of the message signal, which is equal to, you know that, Ka square, power of the message signal is AM square by 2 by 1 plus Ka square. This is AM square by 2. What is K into AM? K into AM is nothing but modulation index mu. Mu square by 2 by 2 plus mu square by 2, which is nothing but 2 cancel. Now mu square by 2 plus mu square by 2 plus mu square. This is the figure of merit of AM. Okay, note down. Okay. Now similarly for any modulation, any analog modulation technique, you can able to solve. Okay. Now let us take, this is FM modulator, FM wave. So now this is S of t of FM, which is equal to AC cos 2 pi FCT plus 2 pi KF integral m of t dt. Now this is S of t, and noise power is same. Now this is FM, wideband noise. Now this is FM, wideband noise. Now this is FM, narrowband noise. Wideband noise is passed in band pass filter, narrowband noise. Now this is the demodulator. This is demodulator. This is the demodulator. Now what is a demodulator? Now the demodulator here is a frequency discrimination method, balancer soap detector, right? And ratio detector or phase lock loop, and number of demodulators. So now see here, now if you do this one, the same procedure, figure of merit, which is equal to signal to noise ratio at output you are getting, this is 3 Kf square into Pm by Fm. This is the figure of merit you are getting. So if I simplify this, 3 into Kf square, what is Pm? Am square by 2 by Fm, which is nothing but 3 by 2 into Kf square Am square by Fm, which is equal to 3 by 2. What is Kf into Am? A Kf into Am is nothing but Kf into Am is frequency deviation square by This is Fm square. So delta F square by Fm square. So can I write like this? 3 by 2 delta F by Fm. Delta F by Fm is a modulation index square. Therefore, this is nothing but 3 by 2 into beta square. Okay, 3 by 2 into beta square is the figure of merit of Fm. Clear? Now this is PM modulator. Now this is a PM wave AC cos 2 pi FCT plus Kp into m of t. Now this is PM signal, phase modulated signal, PM wave and wideband noise, right? And it is passing through a filter, narrow band noise, and this is the demodulator. So the figure of merit here is Kp into PM. Kp square into PM. Kp square into PM. What is Kp square? Kp square into PM. PM is Am square by 2, which is equal to, what is Kp into Am? Kp into Am is beta square by 2. Now Kp into Am, because in Fm, in PM, phase deviation, which is equal to modulation index, which is equal to Kp into Am. Okay. Now this is the figure of merit of PM, no doubt. So now, previously we don't know the values. We guess that their FM is effect of noise is less, effect of noise is more, like this. But now see here, type of modulation, now which is DSBSC. Now in DSBSC, figure of merit is 1. In SSBSC, figure of merit is 1. In VSB and SSB both are same, is figure of merit is 1. Now AM, figure of merit is mu square by 2 plus mu square, right? Mu square by 2 plus mu square. Now which is mu value is 1, 1 by 2 plus 1, 1 by 3, which is equal to 0.33 when mu equal to 1 for 100% full effect. Now you tell me the figure of merit is 0.3, which is less than 1. The figure of merit remarks. Okay. Now see here, The figure of merit of AM, the figure of merit of AM, which is 0.33, the figure of merit of AM, which is less than 1, the figure of merit of AM, which is less than the figure of merit of SSBSC or DSBSC or VSBSC. Therefore, with respect to noise, DSBSC or SSBSC or VSB is, with respect to noise, SSBSC, DSBSC or VSBSC is good compare with AM. Understand or not? Yes, with respect to noise, these are best compare with AM, because here figure of merit is just 0.33, very less compare with DSB or SSBS, VSB. Okay, that is the reason why AM is the most affected by noise, because amplitude information in terms of amplitude, noise is coming and affect the amplitude. Okay, note on this. Now, FM figure of merit is 3/2 into beta square. Now we'll compare with FM. When mu equal to 1, best one, and figure of merit of AM, which is just 0.33, not 50, just 30%. But when beta equal to 1, you just take, when beta equal to 1, figure of merit of FM is 3/2 into 1 square, which is equal to 1.5. Here is 1.5, here is 0.33, here 33%, here 150%. Therefore, figure of merit of FM, which is very high compared with figure of merit of AM. Figure of merit of FM, which is very high compared with figure of merit of FM. That's why effect of noise is very less in FM transmissions compared with AM transmissions. Okay, very high. Okay, now here it is very less. Now, PM beta square by 2. Come to here. So, let us assume when beta is 10, for example, okay, not, figure of merit of FM is 3/2 into beta square, which is equal, beta is 100 square by 2, 50 into 3, 150. When beta equal to 10, figure of merit of PM, which is equal to beta square by 2, which is 100/2, which is 50. If you compare these two, FM and PM, figure of merit of FM is 3 times of figure of merit of PM. Even if you compare with PM, also FM is very, very high. Figure of merit is very, very high. But practically not preferred, this beta. Practically beta 10 is not preferred. Why not preferred? Because when beta increases, what is the bandwidth? Bandwidth is increases, but bandwidth increasing not acceptable, because bandwidth which is equal to 2 into beta plus 1 into FM. But forget about the bandwidth and all things, just comparison figure of merit. So the figure of merit of FM, which is very, very, very high compared with the figure of merit of FM, PM, AM, SSB, DSB, all these things. Therefore, now you write one final statement: among all the analog modulation technique, then the least affected noise signal is FM signal. Okay, so finally, what is the final conclusion? In all analog modulation techniques, FM has highest figure of merit, and the FM signal is the best one with respect to noise. So the king of analog modulation technique with respect to noise is FM. That's why now we are doing an audio signal transmission, and everything is the best modulation for transmission of audio signal, which is nothing but FM. Okay. FM has highest figure of merit, therefore in all analog modulation techniques, FM has least affected by noise.